We're going to start our discussion of Chapter 30 with Motional EMF. EMF stands for electromotive force. Now, I've introduced the concept of the term EMF in the lab already. EMF in terms of electric circuits. At the time I said it was electro, but it was not really motive, it was not really a force. Well, in this case, it really is motive, and it really is a force. So let me explain how this works. This is not exactly the order the book starts, but I kind of like my order a little bit better. So imagine that we have a magnetic field, and the magnetic field is into the board. And in this magnetic field, I have an electrical conductor. The electrical conductor is some height L. And so this electrical conductor is now moving to the right with velocity v. Okay, so what's happening inside there? Well, inside the conductor, it's really made up of a whole bunch of electrons. So using the right-hand rule, okay, there's a force on each electron, F equals QVB. Okay, since they're electrons, the Q is actually going to be fundamental charge, the electrons, so it's negative. Okay, so that would mean that the force, right-hand rule, to the top, but negative means down. So that means electrons would accumulate on the lower surface, and you'd have lack of electrons on the upper surface. So the upper surface would become positive, lower end would be negative. And so as this thing is moving, you end up getting a difference in charge there. That difference in charge then creates an electric field. Okay, well, we know that that electric field exerts a force on electrons too. The force due to the electric field equals QE. Well, again, it's an electron, so the Q is minus E. Okay, so the result of that is that the motion pushes electrons down, but then now the electric field tries to push the electrons up. So the two tend to balance each other. Eventually, they're going to balance EE equals EVB. Okay. The charges cancel. Okay. And so what we have left is that the electric field is going to be proportionate to the magnetic field and to the velocity. Okay. So we have the electric field proportionate to the velocity and the magnetic field. Well, that's interesting because inside this object now that's moving in the magnetic field, so we got the magnetic field, out here. Okay. And now we have an electric field like that, and we said the height of this thing was some distance L. Okay. And so what that means is, or I could use this big L if you'd like. Okay. So that means that we know that the voltage, big V, integral E dot ds, okay. And so in this case, that integral, the dot product goes away because we're all going in a straight line. Everything's constant, so it's just going to be E times L. Okay. So if I multiply both sides here, E times L, okay, equals V B L, that would mean that the voltage, because this is now voltage right here, so the voltage is going to be equal to VBL. Okay, where this is now little v is velocity, magnetic field, size of the object. And so that gives rise to this voltage here. That voltage is now your EMF. So this is the electromotive force. And so if you have an electrical conductor and it's moving in a magnetic field, it would have it would have an EMF on it. In other words, one end of the conductor is going to be positive, one end is going to be negative, and there's going to be a voltage difference between the two sides. And so that gives you the basic theory behind how motional EMF works.